before we get to the empirical discovery of the Higgs boson,
Mhm.
I'd like to start with the theory.
Okay.
Just how was it found theoretically?
Right. So this dates back to the 60s, before I was born, never mind before I was a physicist. And it's to do with this idea, again, back to this, the divisibility of matter. And can you build a theory that will accommodate infinitely small particles? Because in principle, that means infinity is uncomfortable in nature, right? So an infinitely small particle means infinite energy density on the face of it because it has some energy, and if it's just, it sounds like a black hole, right? It sounds terrible.
Yeah.
Um, so how do you build a theory like that? And as the maths of this was developed, and again back to QED, actually, quantum electrodynamics, it was there's a property called renormalizability, which is a way of removing these infinities. But it only works if the theory is based on a symmetry. Symmetry is called gauge symmetries, technically, but it doesn't really matter. The point is, there's a mathematical principle, which is actually very beautiful and elegant, that says symmetries in nature lead to forces. In the same way, there's actually Noether's theorem that some of your listeners may have heard of, where there's a relationship between conserved quantities and global symmetries. There's also a relationship between local symmetries and the forces of the standard model, and it's a generalization of that, actually, which Feynman and others came up with. So that was a neat trick, but it doesn't allow the force carrying particles to have mass. So as soon as you introduce a mass term, it breaks that symmetry. So that was a problem that people were wrestling with in the 60s. And actually, they thought, and I got told this by Peter Higgs, actually, because I wrote something wrong in the New Scientist, and he said, that's a great article, but they were not even thinking about the standard model, really. They were in the end, the Higgs mainly applied to W and Z bosons, which we can come to later. But they were thinking of particles called pions, which are not even fundamental particles. But it was nevertheless, they were trying to think in sort of in the abstract because it seemed relevant. How would you build a theory with massive force carriers? And they couldn't do it, and it looked like they would need to at some point. And there's a neat trick which condensed matter physicists had already used, called spontaneous symmetry breaking, where you have a theory that's completely symmetric, but the ground state, the lowest energy state, is not. So you can. This is why people talk about wine bottles sometimes with the Higgs. So this shape at the bottom, the Mexican hat thing as well. Sometimes the shape of the bottom of the wine bottle with a lump in the middle. If you imagine a marble in the wine bottle and you shake it up and it's got lots of kinetic energy, it can be anywhere in the bottle. It's completely symmetric. The whole thing is symmetric around the middle of the bottle. But if you stand it on the table and let it settle, it will go off to one side, and then the ground state, when it stopped moving, is no longer symmetric. It's broken the symmetry by moving off. So that was the trick they were hoping would work, right? You could keep the gauge symmetries, which makes the infinities go away, and you could have massive particles because the ground state was asymmetric and had this spontaneous symmetry breaking. And that works in condensed matter, but it doesn't work relativistically, and it doesn't work when you. The problem with it is it produces a bunch of massless particles called Goldstone bosons, which just don't exist in nature. So this was the block that they were dealing with in the 60s, and what Higgs and Broughton Englert, who were working independently in Belgium, also noticed was that in the presence of another gauge theory, and in this case, they were looking at when you have spontaneous symmetry breaking and the gauge theory together, they look like two separate problems, but they actually solve each other. So they worked out that if you have a gauge theory there with massless particles and you have a spontaneous symmetry breaking going on at the same time, then they interact with each other such that the massless particles that were the Goldstone bosons become the extra bits of the other particles that you need in order to give them mass, and it all kind of works out very nicely. And what it boils down to, right, is that the mass of the particles, all the fundamental particles, is not a property they have intrinsically of themselves. They're something they have by interacting with this new field, which we call the Brout-Englert Higgs field, if you like. And it's the interactions with that give them mass. The particles themselves, in the absence of that field, would be massless. But that field is everywhere because it's like nature has a spontaneously broken symmetry. It's what we call a vacuum expectation value, which is like the displacement of the marble from the middle of the bottle. It's not zero. It's not in the middle of the bottle. It's displaced. And that displacement is the equivalent of saying that there's this new energy field filling the universe. And by interacting with that, that's how particles get mass. So to bring that home, so that was kind of sitting there as a necessary ingredient of the Standard Model, and it turned out to be needed to be, as the data accumulated through the 60s, 70s, 80s, 90s, became more and more obvious that this thing had to be out there somewhere, or else everything we were thinking of was wrong. And coming back to the kind of empirical nature of this, you think, how would you detect whether this is right? I mean, you've basically invented this whole new field, filled the whole universe with it, which is great for a theorist, if you like. But and you've done it essentially just to make sure the maths works out okay. But can you get some empirical evidence this is right? How would you know this field is there in the universe, right? And the best analogy with that is, how would you know there's air in a room, right? So there's the room I'm in, there's air in this room. You can tell it's there because when I'm speaking to you, I'm making waves in it. I'm making pressure waves, which is sound waves, and I go into the microphone, and then technology takes over. If there was no air in the room, there's no background field, pressure field, if you like, in the room, then you wouldn't be able to hear that. And that's a very good analogy for what we're doing at the Large Hadron Collider. So if this background energy field, this background quantum field, is present in the universe, then if you hit it hard enough, you can make a wave in it. And because it's a quantum field, that wave is a quantum particle, basically. It's an excitation in that quantum field. That's the Higgs boson. So that's why we were so keen to discover it. It's not really that, we've discovered another particle, very good. It's the fact that this is the evidence that that background energy field is there in the universe, and that is what gives particles mass. And so that was the kind of breakthrough that we were looking for. And it took a long time, should we say.
Well, a couple of things. First, you mentioned Higgs' correction to your article, I think, and
yeah.
He also had just worth mentioning, a very positive comment and blurb on your book.
He did. So, no, he was a big fan of the book in the end, I think. It was really nice. And he's not very he doesn't communicate a great deal these days. He doesn't do email. He doesn't answer the phone. So I was really pleased that he'd read the book even, and to get a positive comment from him was just fantastic.
And then, so bosons are, at least colloquially with us lay people, thought of as force-carrying particles.
Yep.
So I wonder why the Higgs mechanism is not thought of as a fifth force.
Yeah, it's a good question. And in some ways, it is. I mean, it's an interaction between particles, which is what we think of as a force. The difference is, well, the two differences. First of all, boson, actually, what it means is something that has an integer angular momentum. And the force carriers in general have a unit of 1 in some units, and the Higgs has 0. So they are different in that sense.
I see.
But the reason we don't think of it as a force is because the forces of the Standard Model are based on symmetries, as I was saying before. They're based on symmetry groups that you then you apply this gauge principle to, and that gives you the force carrier. The Higgs arises through a completely different route. So the mass of the Higgs in the Standard Model is completely different from the mass of the other forces, and the physics is different because it's not based on a symmetry. The Higgs is kind of added ad hoc with no symmetry behind it, really, whereas the other three arise from symmetries. So in some ways, it's sort of semantic. I mean, the Higgs can be exchanged between particles just like a photon can, so why not call it a force? And fair enough. But there is a reason behind the difference, and it's because of this thing. Some of them are arising from what we call gauge symmetries, and the Higgs boson is not. It's just added on almost ad hoc to explain mass at the end as a separate thing. And as a result of that, doesn't actually have any spin even, and there's other differences associated with it.
Yeah, is the Higgs particle the unique boson with integer zero spin?
Yeah, as far as certainly in the standard model, yes, and as far as we know in nature as well, yes.
Is there some
The unique fundamental one. There are combinations of quarks and things that can have spin zero
right?
as well, but as a fundamental one, yeah, that's unique.
Is there some particular significance to its spin being zero for the mechanism?
Yeah. If it had a direction, then you would break Lorentz invariance. So you'd
Okay.
pick out it's everywhere in the universe. Remember, so you would then break the Lorentz symmetry of the universe, which underlies special relativity and the standard model. So yeah, that would be a big problem if it had a spin.
Mm-hmm.
So it really had to be scalar. Otherwise you have a favored direction in nature that is picked out by the spin of the Higgs.
And then you said we'd come to bosons later, which we did. But what is the precise connection between the Higgs boson and then the Higgs field?
So the Higgs boson is